Hello, everyone. Welcome to this lecture in our studio. This is very, very interesting since I am under quarantine. I actually left the country. I went abroad in Colombia. No, I did not go to Europe, Italy, or anything like that, but still they want me under quarantine because I went to the Florida airport. I was outside the country, etc. So you know how it is. But don't worry, I'm doing okay. I actually almost died of dengue hemorrhagico. I've had malaria, syphilis. No, just kidding, not syphilis. But the other ones, yes, and I always survived. So what are we doing in this part of our studio? So this is basically what we're doing here is we're going to take a look at some of, I'm practicing with this whole new Rstudio online, which we're basically, taping, if you can hear me correctly. This is the first time I've done this under these difficult circumstances, and I do miss the class or the discussions we had, how you people have been great students and you've advanced significantly. But let's take a look at this quiz without further ado. So I already put it up there, as you can see. X, you have to the C, 9,000. Remember commas so we can get it. And I always check to make sure I did this right. So X is basically the income people are making. So I always check, you just hit X. All right, so we have it right there. It did go through. And let's see, Y is another one. And it did go through, so that's fine. So what we want to know is basically, opposed to central tendency, we want to start seeing the dispersion of this data. And that is why I asked for the standard deviant. I like that, deviance, deviation, whatever you want to call it. I like to give it different names. But anyways, we're going to see the dispersion around the mean. So let's take a look at X. So X, when we do the standard deviant, we basically have 27,654, which would be the answer. Then we can do it in Y to see, and remember, Y is how much they're spending, I believe I asked, on groceries or something like that. And then you have a significantly lower one, which is pretty good. And remember, we can also see how this is reflected in the Lorenz curve. Basically, we plot. This was not a question, I don't think, on the practice, but L, capital L, you should know it. And then you want to put X. Oh no, what happened? So we basically want to see, hold on. Oh, what did I do wrong? Who knows? Who knows? Quick. And I always do this all the time. Watch this. It's an error. Oh my goodness. Why is there an error? What do we have to do? Now, I usually like to say, I did this error on purpose so you people would learn from my errors. But I'm lying. I forgot to do something, and that is, what do? We're installing packages. So in order to know the Lorenz curve, which is the inequality, we're going to basically put down the inequality package, and we're going to see the Gini coefficient. So let's see how that goes. Nothing. There it goes. So basically now we want to see, before we do the Lorenz curve, we basically want to see what is the Gini coefficient. Now, can we do it? Inequality. Let's take a look. Nope, it's still packing. Packing successful. So let's see. Let's do this. This one is on purpose. So I swear to you. Let's see the inequality of X first. Oh my God, what do we do? What am I doing wrong? What do I need to do? Well, I have to get it from the library. Even though we installed it, don't forget we have to go back and get it from we don't need quotes here. And it seems to go through because you've got nothing. Now we can see. And one way to know that it's there, I always look up here. See, it's up there. So the inequality is basically the Gini coefficient, which is a measurement, correct, of inequality or equality, whichever word you want to say. But let's see to what extent X, these people that I actually designed, are equal or not equal. So let's take a look. So that's pretty good number. So 0.34, that's pretty good because remember the lower is more equality. So you basically have a decent, now remember the Gini coefficient, it depends. I mean, you could have everyone poor and have a perfect equality. So you don't want that, but at the same time, this is pretty good as far as equality distribution. 0.34, but it depends on what one thinks. But all we now have to do is take a look and we plot again. What do we do? Capital LC, the Lorenz curve. So we start seeing, see, this isn't that unequal. So it's actually pretty good. But let's take a look at the other one. First, we'll do the standard. Here we go. Here we go, the standard deviation for Y. Let's change to Y. And we have a smaller one, only 14,261. So let's take a look at that inequality. And remember, we can just go back up. Inequality Y. Well, 0.43. So you start seeing about the difference between the X and the Y. So here we have basically a greater income inequality. So what we want to know is why. So what's with this? So basically we might want to look at the Lorenz curve again, but this time for Y. Now that was not a question, but then we start seeing, oh, why is it being, taken in this degree? And that's when we start seeing the box plot. So let's take a look at the box plot. Remember what the box plot does. So first we go for X. Wow, that's pretty good as far as a standard. So you got 1, 2, 3, 4 parts. And then you can basically see, is there an outlier? Now, box plots are very important. Because most importantly, is there an outlier? And that was the question, and the answer is obviously no, because you don't have that little dot as I want to see. But I'm going to give you a great article on this, on the use of box plots, because we basically have the minimum, the first quartile, the median, the third quartile, and then the maximum. But you start seeing there's no real one dot that stands out as an outlier that might explain the other issues with the y. So if we want to do basically a box plot now, oops, with y, we see, wow, that's significantly different. And look at that outlier away from the minimum, the first quartile, the median, the third quartile, and then the maximum amount. And then you have this one outlier guy or girl way out here. And that's why it's very important. So I think box plots actually do. So if we go back and see this one, oh, wow, you could say, well, this is somewhat normally distributed. If you see it in Zoom here, it's not too bad. But then you see this one here, and we can make it, zoom it up. Basically, you have that one outlier, which really will affect the data. And understanding outliers are important. I always like to relate it to GPAs. You have a GPA, you fail one class, like this one. No, you won't, because you people are doing great. But you basically, that tanks your grade. So we want to know where the outlier is and how that might affect maybe a Gini coefficient or central tendencies like, the mean and other things. And, obviously it is going to have effect on the SD here. So you basically want to know if there are any outliers, and I think box plots are great for seeing that. So they are very, very useful, which you want to remember for the upcoming quizzes. Yeah. Why, families get more than singles? Yeah. 150, 150. I don't know what's gonna happen. Okay, good. All right, then just send it to me and I'll look at it. I got it finished. Okay, so another thing we wanted to do here is understand the box plot. We did the standard deviance. We basically did the Gini coefficient. Now let's do the correlation coefficient. And that's basically just the COR function. And remember, with just this, we're just looking at to see if there's somewhat of a correlation with this, the correlation coefficient. This is not the coefficient of determination, which is R squared, which gives us a better picture, which to see how much the independent variable can explain the dependent variable. So we're basically looking at this, just you could basically just do X comma Y, and then you have, right, 0.71, which is pretty high because 1 is a perfect correlation. But as we're going to see, the correlation coefficient isn't the best. The coefficient of determination is a little better. That's the Pearson's R squared. We're squaring this. And then we're going to have a p-value, etc. But remember, just for this basic correlation coefficient, seeing if there is some type of correlation, even though it's, for me, it's not the best test, it is an indication that you're going in the right direction. There is somewhat of a correlation. We can do this test here. Why? But remember, we don't have a p-value. We're not, rejecting or accepting rejecting the null hypothesis and accepting an alternative hypothesis. Basically, we're just seeing if there's a correlation between these two variables, which is the amount of money one makes and spending, I believe I said, on groceries. I just created this data. So then you could do these basically opposites, and they have the same answer. So, but remember, when we start doing the LM function and getting into testing, it has to be the dependent variable first. So this is seeing the correlation. So we're on the right track. There is some kind of correlation. We're going to use this data later to see if and test it to see the extent to which there is a the independent variable can predict the dependent variable. And there are also, like we talked about before, confounding variables, variables that affect the data and the coefficients, but we did not take into account. So that is very important. Now we switch to a whole different thing using up here. I put it up here so we have it. Using the dbinom function, what is the likelihood one would get 4 answers correct on a test of 20 questions if the probability of getting a correct answer is 18%. So what we're going to do is run the dbinom here. Oh, wow, we can just hit it up here. And that was 4 out of 20 with an 18% chance. So let's take a look. It's about 21% chance. Remember, the binomial, one of the characteristic is it will only answer for the 1. So this isn't 1 to 4. This is just getting 4 correct. So is it easier to get, say, 5 correct? When I say easier, I meant is it more likely to get 5 than it is to get 4 if it's 18%? And the answer is no. But then if we try 3, is it easier to get 3? That is it more likely, sorry, not to say easier, more likely to get 3? It is. But then you would think, well, it would be more likely to get 2, but then we look at 2, it goes down, the chances. Why? Why is 5 14%, 3 22%, and then it goes down at 17%? And that's because this is just saying, what's the likelihood you will get 3? There's a higher likelihood that one would get 3 than one would get 2 out of 20 questions when there's an 18% chance to get something right. So this is just giving it to you, the one number of the given, which is here. So this seems to be the most likely scenario. The same thing here when we go, now let's say we're interested in knowing all of them. So let's take a look at this. 1, doble punto, 4, just got back from Colombia. All right, now we see the same thing. So it's basically, to get 1 is very unlikely. To get 2, you're more likely to get 2 correct than you are 1. Then up here, you're more likely to get 3, but then it goes down here to get 4. And then by the time you get 5, etc. So this 1, doble punto 4, is giving you 1, 2, 3, 4 individually. So this is 1, this is 2. I don't like how R doesn't tell you, because like, let's say we wanted to know like 1 through 20. You basically want to know, and it doesn't say, oh, this is 1, this is 2, this is 3, this is 4. But anyways, regardless, it's useful, because what happens if, say, for example, you know, you were a landscaper and you wanted to know the amount of, you know, the likelihood a tree not from Arizona would survive the heat, and you plant it and there's a 18% likelihood that it'll survive. What happens if I plant, say, 3 out of 20? Well, okay, there's a 22%, oh, let's say that's 7, let's say 23% chance of basically surviving. So this is useful. Now, let's say someone wants to know the aggregate likelihood. That's where we get, let me give this, the binom. So the pbinom here, we see that there's a 71% likelihood. So that's up here. So when you look at it up here, it's that, here, let me get through here. I put the questions up. Well, what is the likelihood one would get up till 4, answers correct on a test? So that's getting 1, 2, 3, or 4 correct. So you have a 0.71%, and my hunch is it'll just go up, because is there a higher likelihood, let's say, for example, to get at least 5, 1, 2, 3, 4, 5, you know? So there's a pretty high likelihood that you're going to get at least 1 through 5 correct answers on a test of 20 questions. But then let's see, what's 15? You know, there's a perfect chance that you're going to get at least 15, 1 through 15 correct. Now, individually, they're different. So individually, they're different. So if I say, oh, wow, 15, but what is the chance I'll get 15 correct? You come down here, you go 15, right, out of 20 cents. All right, as you can see with the 10th, that's a very low number. You're probably not going to get it. But, you know, regardless, there's a high chance of you getting at least 1, 2, 3, 4, 5, 6, 7, one of those numbers, 8, 9, 10, 11, 12, 13, 14, 15. I think there's a pretty 100% chance you'll get at least something, right? But getting 15, that 115 with the dbinom is very unlikely. It is more likely that you will get, oops, sorry about that, you will get 3. You're probably going to get 3, you know, correct. So that's very, very important to understand as far as these work. So let's take the other one. Sanders has roughly 39% of the delegates. And that's going to be basically the answer. But, oh, no, I was told that at this time, Bernie Sanders would have 39% of the delegates. Currently, he has 5757 out of 1,397 running a binomial test. Which of the following is correct? Now, remember, these up here are not tests. Someone asked that. It was an awesome question. It's not a test, but you're seeing the probability of getting something right. This is the test because we're going to have a p-value. We're going to infer from these statistics, you know, the null hypothesis being the given. So the null hypothesis here is, oh no, I was told at this time Bernie Sanders would have 39% of the delegates. So let's do a binom test. Nothing to unpack here. Simple, you know, 5757. And out of 1,000, now remember, do not put that comma. I always put the comma. And, you know, watch, you know, it's always incorrect. 397 and then 0.39. And then you get, oh no, there's an error. So you got to come back up, hit that, make sure there's no thing. And then, oh wow, there's still an error in my binom test. Let's take a look. Huh. And I figured out why. It's 573. Why did I know, I was thinking that's really high. How could it be that high? But anyways, regardless, yeah, it's 55,700 out of 7. So there's no way. 573. The problem is when I type up here, I sometimes are looking down here to type, but then I hit the button, boom, and up there. So you got to watch out, because here we have our own thing where we can write anything we want up here. That was basically what I was doing. So I was writing up here when I accidentally hit two things that changed that number. So he has 573, comma, 1,307 out of 1,397, and there's a 39%. So let's take a look. Okay, so we hit the button. This is a test. So this is the binomial test we have. So don't forget now the p-value. So do we reject this? Well, the answer is up here. Sanders has roughly, and notice roughly, I'm going to explain that, 39% of the goals because the p-value is higher. Remember, the p-value is higher, so we do not reject that null hypothesis. Now, someone asked a really good question. You know, I thought the null hypothesis was just basically there is no correlation or anything. Let's say gender and income. That's usually true with the hypothesis. No, nothing, there is no. And then let's say we find out men make more money than women. Then we basically reject the null hypothesis, which says there is no correlating factor there, that it doesn't predict gender, doesn't predict income. And then we take the alternative hypothesis that says, yes, you know, women make less money. Gender is a variable. Men make more money than women. But in this case, the is just the given. That's the null hypothesis. Right here is the null hypothesis. So whatever number you get is the null hypothesis, and then we run it, and then if we get a p-value of less than 0.05, we're inclined to reject this null hypothesis. So if you look, the p-value here is not less than 0.05, so the likelihood is that this isn't by chance, that this is the correct answer. Now, is that the exact answer? And this is going to be no, because they're giving you kind of, you know, some leniency. So let's say, for example, if I put 40%, okay, it's still a high p-value and it's getting higher. So is this correct down here? Is this the probability of success? This is the correct answer. I mean, the exact correct answer that it would be 41%. Let's take a look. And it is, the p-value is exactly 1. Obviously, we don't reject the null hypothesis. Why? Well, because they're giving you kind of flexibility here. R isn't going to just say, no, that's 100% not correct. Let's see if it does the same for 38. A p-value of 0.02. So it is, we could reject that because it is lower than 0.05, but not much. And that's one of the things. So we're basically saying, R gives us 39. 40, 41, let's see about 42, oops, let's just say 45%, obviously, right, we're going to reject it. That's not correct. So we're talking in the range of, 38, I'm sorry, 39, 40, 41, and I'm sure 42 will allow us to basically say that that is correct. So it's giving us that kind of range, but this is a test to what extent to say 573 delegates out of 1,397 delegates are 39%. And as we test it, we basically are saying that that's correct. And you can see here, this is the 95% confidence interval, which is reflecting basically this is just basically the range of values that we basically are going to get, to make sure that's the mean of the population. So sometimes it'll be 38%. So let's say, for example, we take this. I'll just take it like that. Get rid of this. Something like that. So it's giving us, okay, we're barely, rejecting the p-value. So you essentially have, let's say 3, 5. Then, okay, yeah, we're not going to reject it. That is correct. 388. So it's giving us a confidence level between this range, which the extreme, which this would be basically correct. And they think with higher levels, as we talked about before, with more sampling, it would be within this range. So you have to remember that. So let's say, for example, I want to say 4.2. I'm sure, see, the p-value is just about, you could reject it. Most people won't probably at that close level, but that's what it's basically saying. Between this area, we are going to reject the null hypothesis. That's about the true population of this sample. So to wrap this up and make it kind of easy is that, the confidence interval is that we're saying we're 95% positive that the answer lies within here. So when you look at the binomial test, which is interesting, the closest it is 41, but it gives us that range, that flexibility to say that that's essentially now, I wanted to mention something, as a lot of people say, with a larger sample, this confidence interval, confidence level is supposed to be more narrow, but we talked about that with sampling and the true population, because if your sample, and we're going to do more of this, so don't worry if you don't exactly understand this. I just wanted you to do the binomial test, but if your sample is larger, they say, oh yeah, your confidence levels are going to be narrower. But what happens if you're doing, as we talked about with the Alfred Landon, what happens if you're just doing more and more of the same sample data, and you're just, basically like a vicious cycle, you're committing the same errors. So like if you did in the 1930s cold calling on telephones and you got more and more people in your sample, does that mean your confidence levels intervals should be narrower? Well, no, because you're basically not drawing from the real population of people. So this is kind of an issue. That's why I love the case of Alfred Landon so much. And I believe it's also when, Dewey defeats Truman, etc. So we have to watch out for things like this. But the only thing I really want you to understand here is this is the binomial test. And this is a test because we're getting a p-value. And as it says, 41 right here is, perfect p-value. So we're not rejecting this. This is basically, as I said, the null hypothesis. This is the null hypothesis. Do we reject it? No, because the p-value is 1 and is not below 0.05. So we're not getting this by chance. But what happens if you say, for example, 573 is only 20% of that, then you're getting a really low p-value and reject it. We know 573 delegates out of 1,397 is not 20%. We reject it with extreme prejudice out of the probability of success here, as we can see, is 41. So we have a test. So let's wrap it up and go over a few things. What the goal here was, what was the standard deviance? That's easy. The SD, you put the X, and then you get it. That's your number that we kind of want to understand. The Gini coefficient, you got to get that inequality package. Then all you got to do is this inequality. Let's see, for X, that's pretty low. So that's pretty good. There's not that much inequality. And then you can just plot it on the Lorenz curve. Let's, so we can look at it in a graph, which we've talked about. Graphs are important. Okay, so that, we can see just looking at it that inequality isn't that bad. But then we see when we plot the Y, something else is up there. Then let's see why, why do we have this? Let's take a look. And let's see the Gini coefficient again for Y. Something's pushing it up. What is it? Let's do a box plot. Y, I spelled it wrong. See that? You always do it. You're doing box plot. Then we see, oh wow, look at this outlier out here. So it's very, very useful. And that's something we did. And when you want to look at the correlation, we're taking a look. Well, let's see if there might be, and then we can test it more so later. X, Y, 0.71, 1 is perfect. That there is, we're beginning to see a correlation here. With the higher income you have, the more money you spend on groceries. Now there might be some outliers in that we're going to get into, but these are basically the answers. So, I missed the discussions we've had, and under these extreme circumstances, we're doing the best we can, and I hope you understand. Please ask in the community forum if you have any questions, because this is very important to see, make sure we're basically getting this right in our studio. But our studio, after a while, with baby steps, it's very easy, and we're going to go over more of these. So please ask questions. I hope everyone's doing well under these extreme circumstances that we are living under. I'm trying to understand how to do this. Yeah, and it's tough. I got my little cheat sheets there. So I'm like, because this is the first time I've done it at our studio. We usually teach the class in person, but online it's not as easy under quarantine. I haven't been out. You're going a little stir crazy and stuff like that. So I hope everyone's doing well. Without further ado, we're going to stop this, and please leave comments in community forum, or if they're more of a personal nature, just email me if you want to talk. I'd like to maybe do some kind of Zoom thing later with the students who have questions.